All right, welcome to Computer and Network Security. Today we are going to talk about PGP. PGP is primarily used for encryption and a number of other things, but it's primarily used in email communication. Not solely, but this is one of the primary uses of PGP. It stands for pretty good privacy, and it is pretty good. And there are a number of advantages for it. Here are 5 different advantages that we have of why we use PGP. First, it uses the best available cryptographic algorithms. We'll talk about some of those in a few minutes. It is operating system independent and open source, freely available. And there is also a low-cost commercial version available. One distinction that I want to make here, not directly related to PGP, but there is a big difference between open source and freely available. Just because something is open source does not necessarily mean that it is free. Oftentimes they go hand in hand, which is why a lot of people sometimes use those interchangeably. However, make sure that you understand that some things that are open source are not necessarily free. They may have paid versions, even if you do get the source code for them. Some reasons why PGP has grown as much as it has. It's available free worldwide. It's based on some publicly reviewed algorithms. You'll notice some of these you're familiar with, and we'll talk about them. It uses for public key encryption. It uses RSA, DSS, Diffie-Hellman. We talked about a few of those. Symmetric key, CAST128, triple DES, IDEA. And for hash algorithms, it uses SHA-1. These are all very popular algorithms, publicly reviewed, so they're known throughout the community. There's a wide range of applicability of PGP, and it is not developed or controlled by a government or standards organization. There has been talk of standardizing PGP. It has not yet happened. It may happen at some point, but it is not controlled by a standards organization. It's not controlled by the government. However, you do see that some of what it uses, the algorithms that it uses, could be from standards organization or even government controlled. There are 4 primary uses of PGP. You utilize it for authentication, confidentiality, compression, and email compatibility. So we'll go through each one of those in a little bit of detail. For authentication, it will utilize hash codes. For confidentiality, we use encryption. For compression, we all are hopefully familiar with some of the compression algorithms like zip or RAR, gzip, tar, and then email compatibility. Encrypted messages can be converted to ASCII strings because that is what email uses, is ASCII strings. So we've talked about these before, authentication, confidentiality. We talked about these when we were talking about our encryption algorithms. And PGP utilizes encryption and it utilizes hash code. So let's look at authentication. So if we want to authenticate a message, so we start off with the sender creates a message. We then use the SHA-1 hash to generate a 160-bit hash code of the message. So we hash the message. We are not encrypting it, we're hashing it. And remember that with hashing, hashing does not allow us to do two-way. So when we hash something, we are just going to get, in this case, a 160-bit code, but we aren't going to be able to take that 160-bit code and then get the message back out of it. So it's just a one-way algorithm, and that's what hashing does. The hash code then gets encrypted with RSA using the sender's private key. So now we're going to encrypt just the hash code with the sender's private key. We then prepend that encrypted hash code to the message. Prepend it, we put it at the front. The receiver then uses RSA with the sender's public key to decrypt and recover the hash code. The receiver then generates a new hash code for the message and compares it with the decrypted hash code to see if they match, and if so, we've authenticated it. So what we have done here is we've used the SHA-1 hashing algorithm to make sure that the message received on the other side has not changed. We're not encrypting the message, though. What we're encrypting is the hash code, but we haven't encrypted the message. That means that anybody along the way is going to be able to read the message itself. The way that we know that it's been authenticated, that we know who sent it to us, though, is that we decrypt it with the sender's public key. And then we get the hash code back out. Then we can compare what's in the message to, we hash the message that we've received and see if the two hash codes match up. And so what we're able to do here then is to make sure that the message that was sent was the same as the message that the sender intended to send, the same as what he or she sent, and we can verify that the sender really is the person who claims to have sent it, since the hash code was encrypted with the sender's private key. Okay, next, moving on to confidentiality. Here are the steps for that. So the first one, the sender generates a message and a random 128-bit number to be used as a session key for this message only. The message is then encrypted using CAST128, IDEA, or triple DES with the session key. So we're using that session key actually as the encryption key into one of those algorithms. The session key is then encrypted with RSA using the recipient's public key, and we prepend that to the message. The receiver then uses RSA with its private key to decrypt and recover the session key. The session key is then used to decrypt the message. Hopefully you picked up on these three algorithms, and one thing that you should notice about CAST128, IDEA, and triple DES is that they are symmetric key algorithms. We learned about triple DES earlier. The other two we might have mentioned, but we didn't talk about them specifically. These are symmetric key algorithms. So the key that we're using to encrypt the message in those algorithms has to be the same key that we're using to decrypt it. So what we've done is we then encrypt the session key, which is the symmetric key, using RSA and the recipient's public key. That means that the recipient should be the only person who's able to get the session key, which is the symmetric key, back out. So the receiver then uses his or her private key to decrypt and get that symmetric key back out, and then can use that symmetric key to decrypt the message. This is very similar to the Diffie-Hellman algorithm. If you remember when we talked about the Diffie-Hellman algorithm for transmitting symmetric keys, but this is just a slight variation on it. It's called the El-Gamal method for key exchange. This is a way that we can exchange symmetric keys over an unsecured network. Okay, so that's how PGP deals with confidentiality. Our next one, compression. I didn't go into much depth on this. One of our textbooks does have an appendix that goes through how zip works. You can probably look that one up also. PGP compresses the message after applying the signature, but before doing any encryption, and we use zip as the compression algorithm. That's the one that is in PGP. And the fourth use of PGP, since I told you a lot of how PGP is used is through email communication. PGP provides the service of converting the raw 8-bit binary stream to a stream of printable ASCII characters. When we're encrypting and we're zipping and we're hashing, we're actually dealing with raw 8-bit binary values. We're not necessarily dealing with ASCII characters. So most email systems actually need the text to come as ASCII instead of just in this raw binary stream. So Radix 64 is an algorithm used for converting between this binary stream to ASCII characters. And then PGP adds on one more thing, which is CRC, the cyclic redundancy check. And we learned about that in our networking class, hopefully. Otherwise, look that one up, just to detect transmission errors. Okay, here is just a diagram talking about how PGP is transmitted, and then how it's also received from the file, and then we go to whether a signature is required, so that would take us to the authentication. We then go through the compression, and then we go to confidentiality, which would be the encryption, and then going to converting it to ASCII from our binary stream. You can see that some of these can be circumvented. So in this diagram you can see that we can go straight from the file. Maybe we don't need the authentication, so we can drop that one we compress it, and then we go to confidentiality. If we don't need that, we can skip that and then just convert it. So this is how PGP works. We can add in or remove both the authentication and the confidentiality. When we go back the other way, obviously it's just in the reverse order. Instead of encrypting, we're going to decrypt, and that's only if confidentiality is required. We decompress instead of compressing. If the signature was required, then we're going to strip the signature, verify it. That was using the hashing. So we would rehash the message after we pulled it back out using RSA. So one thing that I want you to look at with PGP and think about is how many times we would be encrypting if we're going to both do confidentiality as well as authentication. And think about running time of these algorithms as well. And I just want you to compare that to some of our other encryption algorithms, and why do you think that PGP is primarily used in email communication? And is this overkill for email communication, or is this functionality all necessary? Can we skip some of it? Do we skip some of it? Have you ever seen emails that use PGP? Just some questions to think about. Read through the book also. There's a lot of resources on PGP and how it encrypts in the hash algorithm. SHA-1, one of the best parts of PGP in my opinion is that it uses these standardized algorithms though. So it didn't actually have to come up with a lot of different ways. We know how to hash using SHA-1, we know RSA, we know triple des and other symmetric key algorithms, we know zip for compressing, we know how to convert from radix 64. So these are all standard algorithms, and they just all got put together, and we called that PGP. So pretty neat little algorithm here. That's it for this lecture. I'll talk with you all soon.